Okay, so let me begin with a correction on this Christodoulou effect, which I unwisely mentioned last time without properly working it out. And so what I said wasn't right, but let me tell you what is right. I hope. Okay. It's called the Christodoulou memory effect. And there is a nice article, I haven't had time to read it, but there is a nice article by Kip Thorne, which you will find online. I'm assuming it's a nice article by K. Thorne. I realized what I said last time wasn't quite right. If you remember, we considered two particles just moving forward in time in flat space with a small metric perturbation. And I derived this equation that if this was the spatial separation vector, then d2si dt squared, so si is a function of t is the time, d2si dt squared was a half hij, 0, 0 sj. Okay, and as I said, in flat space, and for the spatial indices, you don't need to worry about raising and lowering. If you like, I can write that as hij, but of course hij equals hij. Right, now when we actually solve that equation, since that is first order in the metric perturbation, we treat this as zeroth order. Okay, that's legitimate. What we're going to calculate, so on the right-hand side, I'm going to calculate a zeroth order, i.e. constant. i.e. constant. Okay, so we've just got these two particles in flat space, and in flat space without the hij, they just stay at a fixed separation, both at rest with respect to each other. And what this equation gives us is SI1, right, to first order. First order in H. Now, it's obvious looking at this equation that since this is the time derivative, now it's the partial time derivative of H, okay? But we are, after all, measuring H at a fixed position in space. So this particle will be, well, in fact, this H refers to the H at x equals 0. All right, so this is really, this is the same as d2 by dt squared of hij at the position 0. Let's write it as hij of t at x equals 0. Okay, because the particle's not moving. The partial derivative is not equal to the ordinary derivative, only if the particle is moving, so that x is a function of t as well. But if x isn't moving, we're only evaluating this. This is first order anyway, so we can evaluate the position of the particle to zeroth order. So that's what it means. Now, obviously, this is a second order differential equation, right? And so you can integrate it. And so what you can get, integrate it twice, and you will get that the change of SI1 is equal to 1/2 the change in hij, let's say from, and what I mean here, let me write it out explicitly, hij tf 0 minus hij ti 0. Okay, I've got this second order differential equation for the difference between S and H. You might worry there's also a, when I integrate a differential equation like this, I have to get the homogeneous solution, right? There's a constant and linear in T solution, plus the inhomogeneous solution. This is just the inhomogeneous solution. It's the part where S is determined by the source. The homogeneous part S1 goes like constant plus some other constant times T. That's 0 because of the initial conditions. Okay, so initial conditions are that at T initial, the initial displacement is this, so the first order displacement is 0 at the initial condition, and the first order velocity is 0. So these are all 0 by the initial conditions. So that's the result, that the shift of the particle, the net shift of the particle, is the net shift of the metric perturbation. Okay? And that is why it is called a memory effect, that the particle doesn't undergo zero net shift, it goes non-zero net shift. And this shift of the particle, shift in the particle's position, tells you something about the overall change in the metric. So for example, and this is an essentially nonlinear effect in gravity, even though we've derived it linearly. So let me explain that. If I have a star or some object that explodes, okay? Or no, let's think about gravitational waves since we've talked about that. We've got some source, okay? And we've got these blobs moving around, and they're emitting gravitational waves. Okay? So at early times, at Ti, at initial time, at large distances, we have Hij going like Gm over Rc squared times yeah, I'm just going to write it like that. I'm not going to put any indices on that. This is the magnitude of Hij. Okay, basically, remember, we're working in coordinates which are transverse traceless. When we derive the metric of a spherical object at large distances, we did that in another coordinate system, in the Schwarzschild coordinate system. But in both cases, the metric falls off. The metric perturbation goes like this. So there's a static contribution to the metric, which is just the 1 over r gravitational potential. Now, the point is that when this object, so even though this object is moving around, there's a contribution where this is the total mass. Well, actually, yeah, it's the total mass, which is related to the total energy. So that's something initially. Now, this object emits a burst of, emits gravitational waves for some time. And so let's call this T initial. And at final time, or some later time, I'm calling that Ti, Tf. At large distances, the Hij goes like Gm of Tf over Rc squared. And what we argued is that these gravitational waves carry away energy, right? And that was this funny argument that you take the nonlinear term in the Einstein tensor put it on the right-hand side of the Einstein equations. And that's the energy in the gravitational waves. And so the point is that these two numbers are not equal, right? Initial mass and final mass are not equal. It's radiated its energy away. So the long-range metric changes. Okay, and that's precisely what this thing measures. So the delta SI goes like, and I'm not going to worry about indices or coordinates or anything. Just going to give you the magnitude. GM of TI minus M of TF over RC squared. That's why it's a memory effect. It's remembering what the initial mass of the body was. Okay, so that's the Gristadulu effect, explained sketchily but hopefully correctly. Are there any questions about it? Notice that you do not get this effect in electromagnetism. Okay, I was wrong on that. Electromagnetism is a linear theory. And if you have a charge, charges in electromagnetism certainly don't radiate away, whereas mass does radiate away. In general relativity, mass is carried away by the gravitational waves. Okay, so are there any questions about that? Here. Right, so I promised you we would fall into a black hole. So let's do that now. First of all, let's consider a straight particle. And we're going to pick a radial trajectory, so the particle literally is just going to be dropped straight into the black hole. And so if you look at so for radial orbit, J equals 0, no angular momentum, and the statement that G mu nu U mu U nu equals -1, it's going to be a massive particle. Reduces to dr dTau squared plus 1 minus 2 gm over r equals E squared equals constant. Remember where all these terms come from. This metric has a 1 minus 2 gm over r. Then you have a t dot squared, there's a minus sign, plus a 1 minus 2 gm over r inverse r dot squared. For radial orbits, of course, d omega is 0. So this is 1. So you multiply through by, then you say the energy is equal to 1 minus 2 gm over r t dot. Replace this term with E squared over this factor, multiply through by this factor, and you get exactly this formula. Okay, so the first point to notice, this is just what Newton would have written down, right? Newton would have said kinetic energy, potential energy, constant. And the 1 doesn't make any difference, just a contribution to the constant. So unlike photons, you see, photons we saw respond to the stretching of space. The correction, sorry, I'm wrong. The angular, the elliptical orbits, right? When we did the perihelion shift of Mercury, we saw Einstein's correction, but that depended on the angular motion. And that depended on J. When you do radial orbits, it's just as Newton would have said. So the solution to this equation, it's a nonlinear equation, but it can be solved exactly. There's a parametric solution, and I'll just write it down. You can check it if you like. That R equals R over 2, 1 plus cosine theta. So R is a function of theta, but tau, the proper time, is also a function of theta. Tau is equal to R cubed over 8gm to the 1/2 theta plus sine theta. Where R is the initial radius. Okay, so to prove this is a solution, just calculate dr in terms of d theta, calculate d tau in terms of d theta, calculate dr d tau, which is the first thing minus divided by the second thing, plug it in here, plug in this, and you'll find this is a solution. What this is, of course, telling you is that if you graph R against theta, right, theta equals 1 is, sorry, theta equals 0 is where R is maximum. Theta equals pi or minus pi, R equals 0. Okay, so this is R of theta. And tau is this function of theta. So if you try and plot that function, we'll first plot the theta term, which is like that. And then the sine theta just represents a wobble on top of the theta. So the wobble is biggest here, and it's 0 there. But the function is still monotonic. You can check that. So this is t. Okay, so this is t. So if you need to know R as a function of t, read off t, read off theta, read off R. So this solution, not surprisingly, was discovered by Newton. And just represents the motion of a radial particle in Newtonian potential. And so in particular, if we start off the particle, particle starts at radius R equals R at theta equals 0. And at what value of theta does it hit 0? So it hits R equals 0 at theta equals pi. And then we can just read off what tau is. And tau is equal to pi times pi over 2 times say pi equals 2. Right. Pi over 2 times R cubed over 2gm to to the 1/2. Okay, so I just pulled out a factor of 4. And so in particular, if r, the initial radius, is equal to 2gm, the Schwarzschild radius, then tau is equal to pi gm. Okay, so that's the time it takes you, the proper time it takes you to fall to the center of the black hole. And in units, tau is approximately 10 to the minus 5 times the mass of the sun seconds. So for a black hole of mass equal to the mass of the sun, you've got 10 microseconds before you hit the singularity. For the black hole in the center of the galaxy, you've got about 10 seconds before you hit the singularity. Okay, so that whole calculation we did in terms of tau. You'll notice I eliminated t. T was kind of a fishy coordinate anyway, because as I fall towards the horizon of a black hole, t goes to infinity. Okay, and we're going to explore this more. So t was a bad coordinate, but tau is certainly a good coordinate, because tau is the proper time measured by the particle. So if you're an astronaut and you look at your watch and you say, whoops, I fell inside the Schwarzschild radius, tau is the time you've got on your watch till you hit the singularity. Okay, so this is, okay, so now let us study the geometry of the Schwarzschild metric in more detail. And hopefully get clearer the various problems in the coordinates. So I'm going to write down the Schwarzschild metric, and this is my notation: alpha dt squared plus alpha inverse dr squared plus r squared d theta squared. Let me just write this angular part as d omega 2 squared. That means the metric on a 2-sphere. In fact, I'll drop the 2 because it's obvious. It's just the metric on a 2-sphere, d theta squared plus sine squared theta d phi squared. And where alpha is defined to be 1 minus rs over r, and rs is 2g m over c squared, is the Schwarzschild radius. Okay, so that's our metric, and it involves a single parameter, which is rs, and we're going to learn about this metric. Now, this metric is obviously singular at 2 places. All right, r equals rs, in which case alpha vanishes, and this term goes to infinity, and also r equals 0, in which case alpha goes to infinity, and this term is infinity. But it's a solution. It is a solution of r mu nu equals 0 for all r not equals to 0 or Rs. Okay, so it's a good solution of the Einstein equation, so we should study it carefully. Our objective in this lecture will be to connect the exterior solution, which we believe describes the exterior metric of the black hole, to the interior solution, the solution where R is less than Rs. So we want to connect the solution for R bigger than Rs to the solution for R less than Rs. But note that for R less than Rs, R is the time, or R is a time-like coordinate. R is time-like. What does that mean? It just means that the term involving dr squared is negative for R less than Rs. So when we go below the Schwarzschild radius, R is the time, and T is a radial coordinate, because this coefficient is positive. R is time-like, and T is space-like. So connecting these two parts of space-time is not going to be that easy if we remain in these RT coordinates. So here's a picture of it. Here's T and R. And then we have Rs. And a good way to understand the properties of the metric is to look at the motion of light rays in this metric. So out here, the Rs over R is small, and basically you can have radial light rays which are either going in or going out or going in any angle, and they'll look just like they are in Minkowski space. But as we come in, okay, so obviously the way to analyze this is just to look at this part of the metric and set it 0. And what you see is that dr is plus or minus dt. This is in Minkowski. And that tells you the two rays, one of which is going in and one of which is going out. So if we do it in Schwarzschild, so this is radial light rays. In Minkowski, in Schwarzschild, we have dt is plus or minus dr over 1 minus rs over r. Okay, just setting the first two terms to 0 and relating dt to dr, taking the square root. And so this is equal to plus or minus dr times 1 plus rs over r minus rs. Okay, so that's and you can see what the effect of this term is. It's as you come in towards rs, this term is diverging. So the slope of these things grows towards infinity, right? Both the in and the out. Let me just draw the picture, and then you can ask questions. So as I come in, the slope of the light cone in these coordinates steepens and the slope goes to infinity as we hit RS. So the speed of light in these coordinates goes to infinity.
You provide dt equals just 1 over, so dr over 1 minus r slash f of b, so it's whatever it is.
No, sorry, I did it 2 steps at once. So I've got minus 1 minus rs over r dt squared.
Oh, sorry.
Plus 1 minus rs over r inverse dr squared equals 0. So I can set this equal to that. And then I divide by this. And I take a square root. That becomes a 1. OK? All right, no problem. So in Schwarzschild, these are the ingoing and outgoing null rays, light rays. And you see they're becoming very sick in this TR coordinate system. The whole light cone is being squished to a line, okay, at r equals rs in these coordinates. Now, conversely, if we start on the inside, if r is less than rs, you see r is the time. Right? So when I draw my light cone, and t is the radius. So when I draw my light cone on the inside, the whole point of the light, well, one of the points of the light cone is to distinguish the time-like from the space-like directions. And inside r equals rs, r is the time-like direction. Okay, so let me try and draw it away from the singularity. So let's pick some point here, which is far from either the singularity or the Schwarzschild radius. And then as we get closer to the Schwarzschild radius, this guy gets flattened, okay, to just squash down to, get squashed down to a disk in the opposite way than it does on the outside. So in both cases, as you approach RS, the light cone's going very weird in these coordinates. We'll understand why this is happening when we solve for the motion of a light ray. Okay, and in fact, what's going to happen is when we follow a light ray, it is going to sail off to plus infinity in the t-coordinate. All right, and then it will come back from infinity, and it will come back in this negative direction along this null ray. Okay, so imagine this squashed light cone way up at infinity. The light ray will come back, and it will come through here, and it will hit r equals 0. Okay, so all this is just really a sign of that these are bad coordinates, but it will tell us how to pick good coordinates. So now this we can integrate. So for null rays, we can integrate this equation. T equals plus or minus r radial null rays. Okay, we've assumed no angular momentum. T equals r plus rs log r over rs minus 1 plus constant. Okay, so that's the solution. I'm just integrating this dr over r as a log. And of course, that's only a real number if r over rs is bigger than 1. So this is the solution for r bigger than rs. Okay, so for r bigger than rs, that logarithm is real. But you can see what's happening. As r decreases to rs, this log is going to infinity, and the t-coordinate is going to either plus infinity or minus infinity. But for r less than rs, I certainly can't use this expression because the log would have an imaginary part. So I have to choose the other branch of the log. So I will choose r plus rs log 1 minus r over rs plus constant. Okay, so that's the shape of the curve. And as I said, for an outgoing light ray, for example, it will start off doing this, and then as r approaches rs, this log is going to blow up, and the coordinate t will go to infinity. Okay, so this is for r less than rs. So let us pick let's focus on a ingoing. Let's focus on an ingoing null ray. So for ingoing null ray coming from ingoing null ray, yeah, I think it's, let's call it an ingoing null ray. What I mean by that is a null ray which comes from outside the black hole and falls into the black hole. And so for that one, we should have t as minus r. Got to pick the minus sign in the first line because as time advances in the positive direction, the radius has to decrease. The radius decreases. So an ingoing null ray looks like this. rs log r over rs minus 1 for r bigger than rs, and of course plus constant for r bigger than rs. And it is minus r minus rs log 1 minus r over rs plus constant for r less than rs. Now let's just check that makes sense. It doesn't make complete sense, of course, because t is diverging, but it may make some kind of sense. As r decreases towards rs, t is minus r, the slope is negative, and t diverges to plus infinity as r reaches rs, because the argument of the log goes to 0. That log becomes minus infinity, but with this minus sign, it goes to plus infinity. Conversely, if we take this expression, which is supposed to be valid inside rs, as I send r towards rs, again, the argument of the log is going to 0. So this goes to minus infinity, and together it goes to plus infinity. And so that's the description of an ingoing null ray in these coordinates. And you go through this funny place at rs where the time coordinate t is infinite. So motivated by this, let us choose a new coordinate. The point is that if we have these null rays, we've got a family of them, right? For different values of the constant, we've got a whole family of these null rays, right? This is for different constants. But you can regard that constant itself as a coordinate, right? Because the constant here is a function of t and r. So why not choose coordinates where you're of, say, r, instead of choosing r and t, which are a square grid in this picture, just choose a grid which is r, i.e. vertical lines, and this combination of t and r. And then obviously in those coordinates, this new coordinate is constant, okay, because that's the definition of it. It's the quantity which is constant on ingoing null rays. Okay, so we choose this constant in effect to be the new coordinate. So let's v equal to t plus r rs log r over rs minus 1. Okay, and that which is constant on ingoing null rays. Okay, so obviously that quantity is not going to diverge because we know that for light rays it's a constant. It's not such a crazy coordinate. If we go to large R, you can see this is just a null coordinate, t plus r. The log is subdominant at large R, and so this is just a usual null coordinate. So now what I'm going to do is I want to pick a single function v, which is the new coordinate. But you notice that the quantity that was constant, I had to flip the sign of the log, of the argument of the log, right? I had to change the sign of the log to make sure this was real. And so now I'm going to do something crucial, which is I'm going to define v with a modulus. Okay? Now, at this point, you sort of yell at me and say, ooh, putting modulus signs in coordinate transformations is a bit fishy. The reason it's a bit fishy is because it's not analytic. Okay? And so you will find all sorts of discontinuities, and derivatives will be discontinuous, and all that if you do put modulus sign. It's not a trivial thing. But the main point is that at this point, we are blaming T and R. We're saying, these are lousy coordinates. Okay? I have to do a lousy coordinate transformation to turn lousy coordinates into good coordinates. Okay? So it's unfortunately what you have to do. So this modulus is necessary. Okay? Of course, this is completely valid away from RS. There's no problem with this at all away from RS. The only place where this is questionable, putting the modulus sign, is at RS. That's exactly the place where the coordinates are suspicious. So one shouldn't worry about it. But just try it and see what happens. Okay, so if we do this, we get dv is dt plus dr. Maybe it's just a little digression. Null coordinates in Minkowski space. Obviously, if I consider radial rays in Minkowski space, it's very natural here to set, with a similar argument, I can set u equal to t plus r, and v equals to t minus r. And then u is going to be constant on ingoing null rays. And v is, let me define it the other way around. U is t minus r, and v is t plus r. U is constant on outgoing null rays. V is constant on ingoing null rays. And so whereas our TR coordinates look like this, the UV coordinates look like this, right? And the metric in these coordinates is just minus du dv. Okay, so that's null coordinates in Minkowski space, very often useful for solving differential equations where sort of things move at the speed of light. So in any case, this v looks like a reasonable coordinate, so let's calculate dv. When you differentiate this away from RS, everything is hunky-dory. And differentiating the log, I just get, of course, dt over 1 minus rs over r. So this is, of course, for R not equals Rs. And the modulus sign or any other ugliness has gone away. And so now I can just rewrite the Schwarzschild metric in the u coordinates. And so ds squared, using v and r as the coordinates, is minus alpha dv squared plus 2 dv dr plus r squared d omega squared. Okay, to see that, just take this ds squared over here, all right, and we're noticing that, and compare it to this expression when I substitute in for dv. So dv squared will give me the minus alpha dt squared. The dr squared piece coming from here. It's probably easier to do it the other way around. Is that obvious? It's not totally obvious to me standing here, but it is true that dv squared, let's just check it. So minus alpha dt plus d, so this is dr over alpha squared plus 2 dt plus dr over alpha times dr. Okay, so oh, sorry, that, yes, that looks right. So here I get my minus alpha dt squared, which is the first term over there. When I look at the cross term, I get plus 2 dt dr over alpha times alpha, so it's plus 2 dt dr. Wait, that's not, yes, sorry, the alphas cancel. And here I get plus 2 dt dr, so the cross term cancels. And then over here I get minus dr squared over alpha squared times alpha, so it's minus dr squared over alpha. Here I get plus 2 dr squared over alpha, right? So this reproduces that term. And so we find in these VR coordinates that the metric is completely non-singular at r equals non-singular at r equals rs. Why is it non-singular? Well, you see, at r equals rs, alpha vanishes. So you might worry that the metric is not invertible at that point. But it's perfectly invertible, because at r equals rs, the metric is this matrix, right, with gtt going to 0 at rs. And then the gvr is 1, 1. And then, of course, 0. There's no dv squared term. And that's a completely invertible matrix. The determinant is minus 1. So no problem at all in the metric in these coordinates at r equals rs. So in fact, these coordinates are known as Eddington-Finkelstein coordinates. Actually, I have no idea why they're known as Eddington-Finkelstein, because Eddington was in the 20s, and Finkelstein was in the 50s, as far as I know. So why did it take 30 years for them to acquire the name Finkelstein? I don't know. some interesting history there. My guess is that Eddington didn't fully understand the significance of choosing non-singular coordinates. And I'm not sure Finkelstein did either. So people were very confused that if a metric looks singular in one coordinates, they were worried it's really singular. Okay, and as we'll see, it's not at all singular. It's just that you had bad coordinates.
Yeah.
Yep.
So when we chose the B coordinate,
Yep.
I see that kind of get rid of the problem that we had like piecewise coordinate.
Yes.
But the singularity still remains there.
Yes, r equals 0 is still singular.
Mm-hmm.
Yes.
Well,
So
R,
alpha goes to infinity.
Yeah, but in defining V and also having then dV, where R equals Rs,
Yes?
we still have a singularity.
Yes, okay. So this is the same statement. You see, this equation is singular at r equals rs. Well, it has to be because this is not analytic.
Yeah.
Okay.
So where does it
So
happen
in
then?
order to, if you've got bad coordinates, I always need to spend at least 10 minutes on this point when teaching GR. There's no way around it. And it always sounds fishy. And my only resolution of it is just to repeat the point again and again and again and again. Okay, and I understand because it is, it's strange at first sight. The point is that the original coordinates are bad. Okay, metric is bad in those coordinates because of the coordinates.
Yeah.
So your only option is to change the coordinates, which are good. But when you change from bad coordinates to good coordinates, the coordinate transformation is bad. That's the only way to take a good coordinate to a bad coordinate, is to do a bad coordinate transformation.
I can totally live with the bad coordinate transformation, but
Right.
I'm just wondering where the singularity.
How it went away?
Yeah.
Well, it should be clear from the top picture. You see in the TR coordinates, I'm studying light rays, and they're all doing this. They're just piling up here, right? Every light ray is piling up here. So if you believe that light rays are a physical thing, there's something wrong with these coordinates. They're just squishing all the light rays off to infinity. Okay, so your only option is to pick a coordinate which is actually constant on the light rays. It cannot go to infinity. And that's what this V coordinate is. It doesn't go to infinity on the light rays. So now you don't have these light rays going off, at much faster than the speed of light or whatever, diverging velocity. Actually, no, it's not. It's TR, so it's zero velocity. I'm sorry. Light rays are having zero velocity in the radial direction in those coordinates. So anyway, so we did this coordinate transformation. If we were clever, we would never mention Schwarzschild coordinates. We would have just solved the Einstein equations, found, there's a solution, and not worry about RS at all. Except that's not quite true, as we'll see. There's still a problem. Any other? Yeah.
When I talk about like T and R, though, it's a pretty physical idea.
Coordinates are not physical. Yeah. Coordinates are not physical, but fine.
So I mean, how can you interpret
V?
apart from I don't see like you're rotating your coordinates.
Yeah. Yeah, that's what you're doing. Coordinates are not physical things. Yeah.
So could we solve for the metric with our first assumptions of spherical symmetry and get this called?
Absolutely. Absolutely. We could just take this metric and plug it into the Einstein equation, and it's a solution. So you could just forget about Schwarzschild coordinates and just say, I look at these coordinates, everything looks okay. Yeah.
So in some sense, it's just irritating and almost intentionally confusing to call these things TRS, whatever, or TR and theta V.
Yeah, true.
It's cruel and
Exactly. It's silly to think of R as a radius. It's not a radius, it's the time. Inside the black hole, it's the time. Why is it called R? It's ridiculous. Nothing to do with the radius. Okay, and that's what happens. You know, you follow this null ray in, and suddenly you discover the light cone is now squished and then stretched in the other direction, and the whole direction of time is, you know, my God, if that's not a bad coordinate, what is? It's a total disaster. Okay, but yeah.
I think the reason that some of us are attached to T is that isn't it true that it is the proper time of an observer that's very far away?
Yes.
Right?
Yes.
So I guess I'm not sure I understand intuitively what you mean by it's not physical. Like when you say, you draw the picture of all these light rays piling up and never actually crossing
right.
the black hole.
That's right.
That is what it looks like from far away.
Absolutely correct.
Even if that's not what you experience as you
Absolutely
cross it.
correct. So when we do finally get to a good coordinate system, all right, which I hope we will, you will see all of that. So once you write the magic good coordinates down, it will be totally obvious that somebody at infinity, what?
It's not the Eddington.
It's not this.
Okay,
no,
so
Eddington-Finkelstein.
Okay.
Eddington-Finkelstein is a little step towards good coordinates. And I'm about to show you another a problem with Eddington-Finkelstein, that in these okay, it's quite hard to yeah, we'll get to it, okay? We'll get to it. So these are not the solution at all, okay? This is halfway. Okay. So in Eddington-Finkelstein coordinates, obviously, in these coordinates, coords, ingoing, this is how we define them. Light rays satisfy V equals constant. Now, note, and this is where things start to get a little worrying about Eddington-Finkelstein coordinates. The choice of ingoing coordinate, ingoing coordinate, V, determines the direction of time. See, we could have chosen outgoing, but we chose ingoing. And unfortunately, this choice determines the direction of time, R. R is the time, and that has a direction of time. Decreasing R can be forward in time, or decreasing R can be backward in time. Okay? And the choice of ingoing null rays determines the direction of time R for R less than Rs. And what it says is that R must decrease. Okay, we saw that on the null rays, that as I follow them in, this family of null rays has radius decreasing, and since R is the time, that means increasing time is decreasing radius in these coordinates for R less than Rs. And actually, for gravitational collapse, that's correct. And again, we're going to see all this in the good coordinates. That when a star falls inside its Schwarzschild radius, it's got no option but to fall to the singularity. Why? Because R is the time. The laws of physics says if you have no option, you have to increase in time. But increasing time is decreasing radius. So in the time we calculated, that's actually the this is the longest possible time you will survive, right? Because if you fall inside a black hole and you decide and you try to travel at the speed of light, or as close as you can to it, it will only decrease the time you spend before you hit the singularity. So your best bet is to do nothing anything you do will actually make you hit the singularity even quicker, right? Because you know if you go at the speed of light, your proper time is 0 along your path. And so that turns out to be the maximal time you can survive, and it's because of this reason. Okay, so this is the physical case for gravitational collapse. We'll see that later. Gravitational collapse. I'm deliberately making you worried and confused. And hopefully when you see the good coordinates at the end of the day, everything will become clear.
Neil,
Yeah.
really quick clarifying question. When you say choice of ingoing coordinate, you
Yes.
mean as opposed to choosing outgoing coordinate?
Exactly.
Not which line of the...
No, sorry. Ingoing as opposed to outgoing. And so now we're going to choose outgoing. And what we'll see is that when we choose outgoing, we're going to reach exactly the opposite conclusion, that radius must increase, that the direction of time is such that the radius must increase for r less than rs. So it's a bit of a tricky business, you see. Suddenly reinterpreting radius as time, which direction is the future? Is it radius decreasing or radius increasing? And the problem with this Eddington-Finkelstein is it's both. Okay. And the resolution of that is that actually there are 2 copies of the inside of the black hole. You thought there was one region of space-time? No, there are 2. Okay. In one of them, time increases with increasing radius, and the other one, time increases with decreasing radius. So that sounds very strange, but that's what is the case. Okay, so now let's consider instead outgoing. Light rays. And so in the same way, we define U to be T minus R minus Rs log modulus R over Rs minus 1. Let me just see if that's obvious. So I just take the right-hand side over there. T take a plus sign in those last 2 equations on the top board. I take the plus sign, take it over to the left-hand side, and U is a quantity which is constant on outgoing light rays. On outgoing light rays. And if we draw these, okay, so here's Rs, R, T, and so in this case, in this case, at large radius, T is proportional to R. Okay, as we come in, this diverges because the light cone got squashed. So this outgoing light ray comes from T equals minus infinity. Okay, and if I choose that modulus sign, basically it connects to a light ray that comes in that comes out like this, also goes to T equals minus infinity. And so now I can do the same trick. I will just dt is du plus dr over alpha And then the metric, ds squared, the line element, is minus alpha du squared minus 2 du dr plus r squared d omega squared. That's also absolutely fine at r equals rs. Okay, but the direction of time r is the opposite. Okay, so here, as I mentioned, the light cones are sort of squished. Light cones are squished in that direction, and time is increasing r. Increasing time is increasing r. Yeah.
Okay, I'm not sure if this. If I put an observer far away from the black hole,
Mm-hmm.
T is his proper time, and in his proper time, he's got a light ray that leaves the center of the black hole.
Sorry, his proper time
In
is?
his proper time, there's a light ray that leaves the center of the black hole.
Sorry, proper time is not a light ray. What do you mean his proper
sorry.
time is a light ray?
In his T coordinate, I guess.
Yes, which is t, which is the ordinary t. So the ordinary t, in the ordinary t coordinate, the clock of an observer at infinity advances in the same way as that
There's
ordinary
a light
t.
ray that's left the black hole with a finite amount of proper T later. That's reached it.
Yes.
I thought, is that implying that light escaping from the black hole or not?
Yes, it is actually. It's implying that, oh, what do I do with that? I need to move it behind the top one. Okay. It went into the black hole. That's exactly what's happening, because this outgoing light ray is coming out of the black hole. So that sounds very strange, right?
Yeah.
We'll see that is true. There is a sense in these coordinates that stuff comes out of a black hole.
But infinitely far in the past.
No, infinitely far in the t past.
Right.
Right, that's right. But yeah, just feel nervous about this. It's all going to get all right. Okay. I want you to feel nervous. It will all be all right in the end. Yes.
So where do we see the direction of time? Why is it that?
Well, because we know far from the black hole that what the direction of time is, right? T is increasing. And I've got my null ray, and it's got to be going to the future of my light cone, right? So I follow my light cone in, and I know this is always the future, all right? And then I follow this guy into RS, and I say, well, it's the same light ray. Light rays only go forward in time. Forward in time must be increasing R for R less than RS. Whereas over there, it was decreasing R.
You're identifying them as the same light ray because they have the same coordinate V.
Absolutely. Yes. I went to a good coordinate system. Over there, it was V. Over here, it was U.
U.
And I say, these are good coordinates. It's the same light ray. A light ray doesn't reverse its direction of time. And so they must be the same. Only problem is they disagree. So what's going on? The resolution is, as I said, that there are actually two versions of the space-time for R less than RS. One which has increasing radius as the time, and one which has decreasing radius as the time. And in fact, the one that has increasing radius as increasing time is really a white hole, not a black hole. Okay, and so the resolution And you know, this you would only turn to in desperation, this resolution. And that's why it took however many 40 years for people to realize it. There are two versions of the region R less than Rs. One is the black hole, and the other is a white hole. Okay. Nevertheless, they coexist. Okay, and we'll see how they coexist. There's just got to add another region to space-time. We'll see how that happens. Now, in fact, it's worse than this. Okay. Because in ingoing coordinates, so let's imagine we just discarded the outgoing guys and we said that something pathological about outgoing. In ingoing coordinates, we also have a second outer space, meaning R bigger than Rs. And to see that, so let's see, what light rays did we pick? You see, yes. So the light rays we've studied so far were ones where V is a constant. Okay, but there's another set of light rays, obviously, which are the opposite ones. So in ingoing coordinates, we have the light rays, two sets of light rays, of radial light rays. dV equals 0, and the other solution to ds squared equals 0, which is dV equals 2 over alpha dr. Where can we see that? Here we go. So set these two terms equal to 0. And so one solution is dV equals 0. The other solution is dV is 2 over alpha dr. And so this tells you that V is 2 times R plus Rs logarithm of modulus R over Rs minus 1 plus constant. Okay, so this set of light rays are not constant in the V. V is not constant for those. And so V is equal to T plus R plus Rs log mod R over Rs minus 1. And of course, we shouldn't be surprised by this. This is exactly what we wrote down a long time ago, because V is, and this was definition of V, and the outgoing light rays are up there. So we've given T. So you can just substitute that T into the formula here, and you'll get this formula. So we know which light rays these ones are in the T coordinates. And in the TR coordinates, these ones are. So we've studied ones that come in and do this, right? These were the ingoing ones. But now there are also other ones which come in like this and do that. Okay, so this is the second set. And do you see anything funny about these light rays? So we've got all these ones, which we studied, the ingoing light rays, right? They were all a bit sick in these coordinates. We went to the VR coordinates. We look at the second set of null rays. We know what they are. They're just these guys. Anything funny about these guys?
Aren't those supposed to be the outgoing light rays? Why are we drawing them as ingoing?
They're going backwards in time.
They are, yeah, exactly. When you choose ingoing coordinates, you know, that was the definition of V. The V is this function. So I just go to those coordinates, and I look at the null rays in those coordinates, and I find that there's some of them which are going backwards in time. Okay? They are going forwards in. You see, when I say that, what I'm really saying is the following. I think I've decided that R decreasing is increasing time in these coordinates. Right? I decided that this must mean that R, because these radial null rays fall to R equals 0, it must be this is the direction of increasing time. Now that's fine for these null rays, because if I trace them back, they're increasing in time outside the black hole. But there's another set of null rays which satisfy that they're increasing time for R less than Rs. But when I trace them back, they came from null rays that were decreasing in time as they're falling into the black hole.
Shouldn't it be the other way around?
No,
The lower ones going, the arrow is just opposite.
Well, you could draw it this way, and then you would say that according to these null rays, increasing radius is increasing time. Well, you can't have it both ways. We already decided decreasing radius was increasing time. So we have no option. We've got to draw the arrow this way. This is increasing time. And then the problem is, if we draw the arrow this way and trace those light rays back, we say, whoops, they came from light rays that are going backwards in time outside the black hole. And the only resolution of that, that's a real problem for Eddington-Finkelstein coordinates, and the resolution of it is that there is, guess what? Resolution. There are two versions of the region R bigger than Rs. Now that's really shocking, okay? Because R bigger than Rs is the whole universe. So what this is saying is there's a second universe. Okay? In the Schwarzschild metric, there's a second universe. It's not just that I have two copies of the interior of the black hole. I've really got a second universe, all right, too. A whole new universe.
It sounds like the second one's a copy of the first one, since everything's moving backwards.
Well, you can't have the two, if they both exist, and they're both legitimate, and I can follow particles out of them or into them. So again, when we study the Schwarzschild metric, unfortunately we've gone a bit slowly. When we study this Schwarzschild metric, we'll do this next time, in good coordinates, we'll see indeed this is the case. That according to the Schwarzschild metric, there really are in good coordinates, there are two copies of the interior and two copies of the exterior. Yep.
What are these good coordinates? What are good coordinates? Do you double?
The good coordinates are the Kruskal coordinates. Of course, there's an infinite class of good coordinates, but Kruskal was the person who made sense of all this. So Martin Kruskal was an undergraduate who read some relativity books and fiddled around a bit with the Schwarzschild metric and found some coordinates which have none of these problems. Okay, and as you'll see, it's really not a difficult calculation. And he didn't think it was important. And then I believe he met one of the famous GR people like John Wheeler or somebody, and he said, "Oh no, there are coordinates." And John Wheeler said, "Oh, that's very exciting. So you must write a paper about this." So it is a funny situation because general relativity wasn't a very popular subject. Its heyday had been, 1920, when Eddington led an expedition to confirm the deflection of light. And he went to Africa, and he measured the deflection of light by the sun, and it confirmed GR. And then the other tests were so difficult. Gravitational waves were just impossible to detect. They're so weak. The people just slowly lost interest. A few formal people worked on it, like Bryce DeWitt worried about quantum gravity a bit, and John Wheeler, and they invented the Wheeler-DeWitt equation. But the subject became very disconnected from physics. Very few people were pursuing it. And so somehow these sort of paradoxes survived in the literature. Nobody really understood what the hell's going on in the Schwarzschild metric. They didn't really understand the point which I kept repeating, that if something is bad, first option, blame the coordinates. Okay? Do a bad coordinate transformation where the badness is exactly where the metric is bad, in the hope that after this coordinate transformation, you'll have a good metric, good coordinates and everything, and then you'll just say, the other coordinates are just bad coordinates. So that should always be the first line of resort, is blame the coordinates. If you find something which is independent of coordinates, which is bad, as you do at the singularity, r equals 0. So for example, if we calculate the Riemann tensor for the Schwarzschild metric, and actually, let's go through this. What should I use to tell that the Schwarzschild metric is bad? I want some scalar quantity. I want some quantity which does not depend on the coordinate system. Ricci scalar. Is that a good idea?
Yeah.
No.
What's the Ricci scalar for the Schwarzschild metric?
0.
Yeah. Schwarzschild metric has Ricci tensor equals 0. So Ricci scalar is 0. So that's very good at the singularity. 0 not singular. What else can I do?
Take contractions of the Riemann tensor?
Yes, so that's a good idea. So we calculate the Riemann tensor. Now it's a tensor, therefore coordinate dependent. So let's contract it with something. That is a real coordinate scalar. If that's infinity, no coordinate transformation is ever going to change it. And when you work out the Riemann tensor, we can probably see, you see the metric. The metric is diverging like 1 over r. The Riemann tensor is 2 derivatives of the metric, so it will go like 1 over r cubed. You square it. This goes like 1 over r to the 6th as r goes to 0. And so nothing you ever do will change that. No coordinate transformation will change that. But when you calculate this quantity, it's finite at Rs. So, and all curvature invariants are finite at the Schwarzschild radius. That's an indication that this is really a coordinate problem. But the trouble with this method using curvature invariants is that what's the right way to say it? The simple way of saying it is that there is no description of gravity or GR which doesn't use coordinates. You're just stuck with using these things. You know they don't mean anything. It's just because we can't calculate geometry on its own terms. We've got to introduce these numbers. And we use these numbers. We know they have all kinds of problems, including coordinate singularities. And in different situations, which numbers you use depends on which are the good coordinates for the problem you're looking at. So it's just a basic deficiency in our description of geometry. Any other questions? Yeah.
The inconsistency in determining the time came
Yeah.
from identifying light rays outside and inside the black hole. What if we just say they are different light rays, and that the outside ones never go in and that the inside ones never go out, and those are just separate regions?
Yeah, that's pretty ugly, right? That's just saying that I'm going to take a razor and slice the universe down RS. And then you have total disaster, because then you have no idea what comes out of a black hole. See, these light rays come out of a black hole in finite affine parameter, right? So you're just chopping them at some affine parameter. And what the result of that is you've got a theory that's completely arbitrary, because you're free to just stick light rays coming out of that at any time, and you can't predict anything. So black holes would emit stuff with an unpredictable rate. Yeah.
It's also that, I mean, why there's even this whole confusion in using TR coordinates is because there's a discrete isometry where t goes to minus t, and nothing happens to the Schwarzschild metric. So
say again, there's a discrete isometry between t goes to minus t. Yeah.
So we get confused because when we draw it in TR coordinates, we don't realize that actually this isometry is not, it separates into different patches. We need different patches to cover them. The patches just are identical. So
yes,
that's the confusion.
Yes. No, that's right. I mean, these coordinates, you're trying to cover a big space with coordinates in which the different pieces of that big space are represented as the same.
Yeah.
But actually, they're not the same. They're really different parts of space. That's right. I think that's what you're saying. So we will see that next time when we do the Kruskal coordinates. As I say, they're really, the obvious thing to do here is I've got U, which was good. I've got V, which was good. But they have this funny time problem. Just put them together. Okay. Give up T and R altogether. All right. Use U and V. And when you put U and V together, that's what Kruskal did. And then everything is fine. But you've got these extra regions of space-time. Now, just to warn you, this new universe doesn't really exist. Okay? Neither does the white hole exist. When you solve for a collapsing star, only the metric outside the star is described by Schwarzschild. That will end up in the Kruskal coordinates as describing the outside of the black hole, the inside of the black hole, one copy of each, and no problem apart from the singularity. Okay. All right, so we'll continue this next time. Is there class this afternoon?